So today we're going to cover the second and third laws, really basically talking about entropy, and then we'll get into the state functions and talk about just some of the material properties that we get out of thermodynamics. So the one on state functions is really like there's not a lot we're going to be doing with that chapter, so it's okay if I just hit the high points on it. And then if you want a longer video on that, there's one on YouTube on that that just goes into more detail. But we'll just hit some of the high features of that particular lecture today, and so we'll be caught back up. Okay. Yes, is it not going? Oh, it jumped off again. It was. Thanks. And Paul, if you hit that middle switch. Yes, thank you. Okay. And so we've talked about heat capacity. It's only when I turn around, right? So, all right, so let's try this. Settings, projector's on. Unplug it and plug it back in. This is universal fix for everything. Blink, blink. Okay, very good. So let's talk a little bit about this idea of heat capacity. We beat this drum quite a bit in this course, and then we'll compare that to specific heat. So we hear these things used interchangeably. So when it's heat capacity, when I use that term heat capacity, it's going to be per mole. And so like for polyatomic gas, we go through and we do the 6 halves R, it ends up being 25 joules per mole Kelvin. For water at room temperature, it's 72 joules per mole Kelvin. But then the specific heat, you'll hear that a lot too, and that's per gram of material. Now, what I don't know what to do with is when people say the specific heat capacity. And you'll hear that too. You're like, you're breaking my brain. Which is it, per mole or per gram? So specific heat, physically, they're talking about per mass of material. Okay. And then when we are talking about changes in energy, if you're looking for the notes, these 2 slides were pulled from the previous one. So since we didn't cover them, they were kind of at the end. So I'm pulling those back in just to make sure that we cover those. So it's like the last in the last section of notes on the previous set, the first law set. So when we're talking about internal energy, we can look at the temperature change, which gives us that change in internal energy using the heat capacity at constant volume. The heat capacity at constant pressure will give us the change in enthalpy. And so that's, we can use that temperature change to understand what's happening to the energy of the system. And so since work is 0 with constant volume, this change in temperature is telling us the heat input. Work is 0, so delta U is CV delta T. That's one of our fundamental equations that we're going to use a lot. So I'll do a summary of equations here in a sec. So here's our summary of equations. We had that irreversible expansion, so expansion against a constant pressure. And then we had this conversion factor. Remember the ratio of the 2 R gas constants. And so this was 101 joules per liter atmosphere. And so that's a very useful thing. So this is all note card bait here. You definitely want to have these on your note card and labeled appropriately, like irreversible expansion or isothermal reversible expansion. Yeah, I'll go ahead and snap a photo of that. And so here's the work associated with that. And then that constant volume, the change in internal energy is the number of moles times that heat capacity times the change in temperature. Then we have enthalpy at constant pressure. It's the heat of reaction, and so it's going to be this constant pressure heat capacity. And we'll see how those are related down below. Okay, so if we wanted to know the change in enthalpy, we could use that same equation, but instead of CV, we use CP. And then here's the relationship of CV and CP. So remember, we used all of those different multiples of R for the heat capacity at constant volume. You just add one more unit of R to CV and you get CP. Okay, so this is pretty easy to do. So this is a review of all of our equations up to this point. And so then here's our second law of thermodynamics. it's changed. I've added one word to this definition from your notes, okay? It says no cyclic process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. That would be nice if we could pull that off, because if it was a cyclic process that turned heat into work 100%, then we could have a perpetual motion machine. Okay. But we can't. We have to use entropy changes, and the entropy of the isolated system must increase in a spontaneous process. So if we want our motors to work spontaneously, then we have to increase the entropy. And that's what essentially is in the form of heat. So we have to use some heat, as I call it, the entropy tax. We got to give some heat to entropy for the system to be spontaneous. Okay. But let's look at this reversible isothermal expansion that we had last time. Okay. And so here's our work associated with that. And again, it's this, we're getting this area under this curve. Okay. And then that change in internal energy, it's the number of moles times delta T, but that's equal to 0 because delta T is equal to 0. It's isothermal. And so this is some of the things that you need to have sort of I wouldn't say it requires a spidey sense, but you need to be able to understand when you say isothermal, that means this is equal to 0. So when we're going down this hill in a reversible way, we're staying right on the same temperature. We're expanding, so we're doing work on the surroundings. Expanding gases tend to cool, right? Okay. But what's happening here is that the change in internal energy is 0, but that doesn't mean that Q and W are 0. That just means that work, which is a negative number, we're doing work on the surroundings, is equal to the opposite sign of the heat, which is a positive number that's coming in. So for reversible isothermal expansion, we are converting heat directly into work. So it seems like a violation of the second law, right? It's a process which turns heat directly into work. But it's not a cyclic process. So what would happen if we ran it backwards? We would come back up, okay? We would do work on the system to reset it. It's isothermal, so we have to suck the heat back out of it. And so we've come back up to our initial system. We've gone down the hill and back up the hill, but the work we got out of it, we had to put back into it 100%. So if we got 16 joules of work out, we had to put 16 joules back in to reset the process. Okay, so it's not a very exciting cycle. Okay, we didn't get anything out of it. What we got out on the expansion, we had to put back in on the compression. So how could we make this system produce an amount of work that was non-zero? See, we went down and back, and the work out and the work in are equal. So when you go around the cycle, it's 0 work. So we got no work. And we got heat out of it when we reset it, but we put heat in when we did the work. And so our heat is also 0. So we reached that. We haven't done anything net-wise. So in order to make a cycle, we have to have 2 different isotherms. And so we expand on a hot temperature, and see this temperature here, this is a high, okay? If temperature's high, we do more work. So we get a lot of work out of the system here. So work less than 0, right? It's negative, means it's putting work out, okay? And then down here, work is greater than 0. We're resetting the system. Right here, we've got to drop down to this isotherm. So we have to rapidly cool the system at a constant volume. Work equals 0 because it's a constant volume. And then going up here, work is 0 because it's a constant volume. So we've made our first cycle. Okay. How might we do this? Well, we could sort of pop the valve on our piston and let all that hot gas leave and put in atmospheric gas, which is cold, and compress it. okay? And then over here, we could like burn the gas in a constant volume and create an enormous amount of pressure, okay, without expanding anything. So over here, we could burn the gas, raise our temperature, get a higher pressure, and then let it expand, okay? And then down here, we puff the remaining gas out, we put in new gas into the same volume, and then we compress. Okay, so this might actually work. And in fact, this is how a combustion engine works. But let's look at the work and the heat. Down here on this isothermal compression, work is greater than 0, so we're putting work in. But notice it's at a lower temperature. So this temperature is lower, so it's a smaller amount of work in. So it takes a small amount of work to compress a cold gas. And then we get a large amount of work out because it's expanding a hot gas. So we get more work out than we put in, we're good. We have a spontaneous engine that produces a net amount of work. Yes?
Doesn't it still take energy to like run the distance?
Yeah. And so that's we use that flywheel, you know, or like in the old single cylinder, if you ever hear a tractor, sometimes in a parade, it'll be called a Poppin' It goes pop, 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 pop. Because it's such a single cylinder, big cylinder, so it has a lot of torque, but it's just a one cylinder and it has a flywheel on the side. And so it pushes down and uses some of that energy to do the work that you want, but some of that energy is used to spin that flywheel. And so then that flywheel uses some of that energy to do this work to compress the system. But it's a smaller amount of work pushing the piston up than you get when the hot gases push the piston down.
Okay.
And then you have friction losses. Is that what you're saying, that the piston moving causes work?
I just thought you were saying that this is like a way of creating like a constant flow of energy, even though we're using energy to like run the system.
Yeah, and so you have those losses for sure. Yeah. Okay, yeah. But the point I'm trying to make is that if you compress it at a lower temperature, it takes less work to compress. And then if you expand at a higher temperature, you get more work out of it. So the higher the temperature, the more work you're going to get out of it. And then the lower the temperature of your compression step, the easier it is to reset. So in a cycle, you have to reset. You have to get back to where you started. And that's the process that the second law of thermodynamics is saying is not 100% efficient. Okay. So how could we get our work step to be zero, like basically zero work to reset the system? We have to take temperature down to zero. And we're not going to be able to get our cold reservoir to be at 0 Kelvin. So we're just never going to be able to achieve that. So that's our cycle, first cycle problem. It's very similar to the Otto cycle. Okay. So this idea of order to disorder is spontaneous. This is just some background thinking about entropy. You know, we drop a ball and it decreases as it bounces because the ordered motion of the ball is being lost to the disordered motion of the floor. You're actually heating up the floor when you drop a ball on it. Okay, you're increasing the random motions in the molecules and so on. So the total energy of the system, ball plus floor, is conserved, but the distribution of energy is what's driving spontaneous change.
Wouldn't air resistance contribute more to this?
It slows it down some, but it's really the loss of that. Yes. So you could try it, test it. Oh, there's a great way to test that would be to put it in a vacuum and see what happens. And the Ames is a big NASA facility for vacuum testing satellites. So they put these large objects in there, and it's a huge bell jar, concrete bell jar with vacuum pumps hooked to it. And so they could suck the air out of this huge room and vacuum test, their equipment. Well, they did the Newton thing of dropping a bowling ball and a feather in there because they have lots of video cameras and everything. So you can look that up on YouTube. It's Ames Research, Ames NASA facility. And sure enough, the bowling ball and the feather go bam, and hit at the same time because there's no air resistance keeping the feather aloft. So disorder to order is improbable, but not impossible. Okay. So things that's, are at rest tend to stay at rest, right? It's one of Newton's laws. It's not impossible, though, for just some sort of improbable vibrations of the molecules under my coffee cup to just go up at the same time and cause it to bounce. It's not impossible mathematically, okay? It's so improbable we never see that, okay? And so that's what always brings me to this, one of my favorite clips.
What are my chances? Not good. Not good, like 1 out of 100? I'd say 1 out of 100. So you're telling me there's a chance? Yeah.
So there's a small chance that a ball will just jump off the floor, okay? But it's worse than 1 in a million. It's not going to happen. We're not going to see it, okay? So the entropy of an isolated system increases in the course of a spontaneous change. So this total delta S, is greater than 0. The simplest isolated system is the universe. Nature as a whole is moving towards disorder. It's really, like you said, the distribution of usable and unusable energy. You have a compressed gas, that's usable. If you let it all expand, it's unusable. Okay. Gas in a container is usable. Gas outside of a container is less usable, And if we want to compress that gas, we've got to suck it out of the atmosphere and stick it in a container. And that generates a lot of heat. And what that heat does is it increases the entropy of the other gas that's out into the atmosphere. So we are compressing, we're going against entropy there, we're compressing a gas, so that entropy is dropping, but the heat we generate is more and generates more entropy in the surrounding air than what we got. So the delta S is greater than 0 for that process. So for the reversible isothermal expansion of a gas, we have Q equals minus W. And then this change in Q divided by the temperature is the change in entropy. And so we could look at that. And so here's the entropy change for that expansion of a gas. Notice the T is gone from the division, and we have the minus sign is gone. So we can calculate entropy changes based upon expansion or compression. We can calculate entropy changes for phase transitions too. So now if all of the energy is sucked out of the system, of course, the partition function is reduced to 1, and so that entropy goes to 0. We know that from we can imply that even from Boltzmann's equation that's on his tombstone. But this was called the Nernst heat theorem. And since entropy is a measure of disorder, then S should go to 0 as T goes to 0. So that's our third law. The entropy of a perfect crystalline atomic substance is 0 at T equals 0. Now, the practical result is that we now have a reference point, and so we can make tables of our entropies. And so we'll use a standard entropy table here for a simple calculation, just to show you what I'm talking about. So we can look at phase transitions and evaporation and condensation of steam at equilibrium at 1 atmosphere and 373 Kelvin, or melting and freezing of water in equilibrium with ice at 1 atmosphere and 273 Kelvin. With this, there are equilibrium processes, and so our delta G for that process at that temperature is 0, because it's in equilibrium, and again, it's spontaneous forward and backwards reaction, so delta G is 0. And so if that's equal to 0, then the enthalpy of melting is equal to the opposite sign of a delta S. Okay. And so then this entropy of melting is the enthalpy of melting divided by the temperature. So we could calculate then the entropy of all of these different processes, like the exothermic or endothermic processes will tell us whether the entropy change is positive or negative. And so freezing and condensation are exothermic, which means delta H is negative, and they cause a decrease in entropy. Okay, whereas melting and vaporization are endothermic. Okay, and they call it that means they have an increase in entropy, and that makes sense if you think about melting. So you've got a solid where, say, water, all of those molecules are in a crystal lattice, and then you melt it. You've increased the disorder. Okay, you could think of it again, our particle in a box thinking. What's the box for a molecule of water in a solid? It's very small. You put it in a liquid, now it's increased. Okay, then you put it in a gas and it's increased to the room. So boiling is a huge increase in entropy. So here's the math behind all of this, these variations of entropy with temperature, and we end up with this really nice like summary calculation down here at the bottom. And so we have some, entropy at constant zero. You can, for a perfect atomic crystalline substance, that would be zero. For other substances, you have what we call residual entropy. Then you can integrate the entropy of the solid, okay, and that would be your heat capacity of your solid, and integrated up to your final temperature. If your final temperature is the temperature of fusion, okay, if you go all the way up to where it melts, okay, then you calculated the entropy of heating that solid. Then you have the phase transition for melting, so that would be your delta H of melting. And then you have from fusion to boiling. If your final temperature is somewhere in that range, then you just integrate up to your final temperature and you have the entropy at that substance. If you are above the boiling point, then you have to take into account the enthalpy of boiling. And then if you're in a gas phase, then you integrate up to your final temperature of the gas. So you can just build this entropy up with these various calculations. And so if we're way up here, then we've integrated. Now the reason this is kind of a funky shaped curve is because this curve is, again, that CP curve is not linear. And then we have the entropy change for melting. You see it has a pretty big jump. And then we go through the CP for the liquid. Then we have an entropy jump for the boiling. And then we get up to our pressure and our temperature for our gas. So here's some actual experimental data for oxygen. This also introduces a concept that you haven't maybe thought of. In the past, people will say, wait a second, what does solid 1, solid 2, and solid 3 mean? Okay, that there can be phase changes within solids too. So we have phase changes you're familiar with, boiling and condensation, or freezing and melting, but then you can have different solid structures. So if you think about your oxygen dimer, how many structures did you have? You had the rhombic form, you had the tetrahedral form. Some people were able to get the T-shaped or the linear form. If you were to freeze those linear forms out, then they would have a particular 3D shape. And if you cool it down, maybe there's a lower energy structure. Maybe you have a solid phase transition where all of those molecules start taking a different shape. And maybe they have a different density and a different volume then. And so the crystal changes shape and shrinks or what have you, responds to pressure. And so you can have phase transitions within the solid. And so one of these solid 1, solid 2, solid 3s of oxygen, if you were to dig into those crystal structures, you'd probably see some of the things that you did in Excel, like the three-dimensional tetrahedral shape or some sort of planar shape. And so those would be the different phases in the solid that you would have. And they have different heat capacities, different volumes. They have phase transitions as well. So here's the data of the entropy increase for oxygen. Notice the largest entropy increase right here is the boiling. Okay. Over here's the heat capacities. And this is kind of nice. We see the heat capacity increase dramatically with the different solids. Finally, we get to solid 1, and the heat capacity is a constant here, roughly over the temperature range. And we said, the assumption for this equation was that these were constants. If they're not constants, then you just have CP for the solid as a function of temperature. Okay, so then you would just have to have an equation there that would be part of that integral. But for, you know, large or higher temperatures, these CPs are roughly constant with respect to temperature. So this is the solid heat capacity here. This is the liquid heat capacity. And then when we get to the gas, look what it is essentially. 7/2 R for oxygen, which is what we would have predicted from our degrees of freedom. 3/2 R for translation, another 2/2 for the rotation because it's a linear molecule, and then another 2 for that vibrational mode for oxygen. Okay. All right, so then with this table idea, we can calculate entropies of reaction. So here's water and hydrogen and oxygen making water. So you sum up the products and subtract the reactants, and you look everything up in the tables. And so these pure elements must be included, whereas enthalpy and Gibbs energy of formations, which we haven't talked about, we'll talk about next time in thermochemistry, you don't include the pure elements. Because entropy's reference point is absolute zero, even elements are above absolute zero. So you have to take that into account. Okay. So here's our tables. So we have oxygen, and look, there's 3 forms of oxygen here. So you got to make sure you use the correct one. So we're using the 205. Okay. And then for the hydrogen, we're using 130. And then for water, you've got to really be careful here because there's 2 waters. So we're using water gas or water liquid. So we look at the problem. I'll switch back to the previous slide. We're looking at water liquid. Okay. So we're going to use this one. So you really have to pay attention to the phases, and you have to pay attention, of course, to the species that you're dealing with. So here's our calculation. We looked up the water. This is, again, a product, so 69.9 joules per mole Kelvin. We have 1 mole. We have subtracting the reactants, so 1 mole of the hydrogen, 130.7 joules per Kelvin then, and then 0.5 is this 1/2 here. Because in the table, that's for 205 is for a mole. It's joules per mole Kelvin, and we only have 1/2 a mole. So you got to take into account the 1/2 a mole. And we end up with negative 163.4. So this has a delta S equals negative 163.4 joules per Kelvin. Notice there's no mole here. No mole to the -1, because the moles are in the problem, in the equation. You see, so this number is per mole of hydrogen and per mole of water, but it's per 1/2 mole of oxygen. So whenever you write one of these delta H's or delta S's by a reaction, this is wrong a lot of times in books, and I might even, just because I'm going fast, make a mistake, but it's truly a mistake if you see a per mole next to a reaction, because the reaction's telling you they're moles. Okay, now if everything's 1 mole, like everything is 1 mole, then that would be fine. But in this case, not everything's 1 mole. We have a 1/2 a mole of oxygen. So that's the number we get for 1/2 a mole of oxygen. For 1 mole of oxygen, it's double that. So it'd be negative 326.8 joules per Kelvin. If we doubled everything, then it would be for 2 moles of hydrogen and 2 moles of water. And so if you were to ask, like this one would be next to this reaction. So 2 H2 gas plus O2 gas gives 2 H2O liquid. Delta S equals minus 326.8 joules per Kelvin. See, there's no per mole there because it's for those numbers 2, 1, and 2. So that's how you use these entropy tables or these standard thermodynamics tables. This picture is grayed out. I just wanted to emphasize the column where the entropy, but this is going to be one of the handouts you have on the tests. So you'll have the delta H column, the delta G column, the delta S column, and when we get into the next section, you'll have the standard reduction potentials. So you'll use those too. So that's something you'll see in the future. Okay, so let's look at the state functions notes. Again, don't worry if you haven't gotten those printed out. Oh, we missed a top hat, so let's do that real quick. Okay, so which process increases the entropy the most? Is it off?
Yeah.
What? Did it just happen? That's so strange. Maybe I was tapping the tab key a little too hard. Okay. Which process increases the entropy the most? We got 5 choices here. Okay. See how you did. Yay, okay, very good. I like to see that. That's the correct answer. What? That's strange. Okay, so can you think of a process that doesn't, oh, well, let me, anyway. So boiling was the one that increased it the most. Can you think of a process that would generate more entropy than that?
Bomb.
Well, what's a bomb doing? That's good. Yeah, sublimation would be one that, like the equilibrium processes where you're taking a solid straight to a gas, but a bomb as well. You're taking solids straight to a gas. The reason that chemical explosives are so powerful and so hard to stop with external means is because they contain their own oxygen. So you've got an organic molecule that has the oxidation, or it's the fuel and the oxygen in the same molecule. So and you can calculate what they call oxygen balance. And if the molecule has enough or more oxygen than it needs to fully combust, then you've got an explosive. So that's how you can determine if something is an explosive substance or not. You could calculate its oxygen balance. Some molecules don't have a positive oxygen balance, but are still explosive because they contain enough oxygen. But things like nitroglycerin are so explosive because they have a positive oxygen balance, and they're shock sensitive. All it takes is just a small mechanical shock to get them to start reacting. And when they start reacting, then you can't put it out because most of the time we fight fire by starving it from oxygen, okay, or getting rid of the heat. Well, since the oxygen and the fuel are so perfectly mixed, the heat comes out way too fast. There's no way to steal the heat from the reaction. You can have the particles be below what they call the critical diameter, and you can have the particles be in water, which is essentially like a firefighting technique on an explosive. If you have the explosives be wet with water, then it's hard for them to detonate. Okay, so, but as far as the entropy, yeah, so it's the same answer: sublimation or an explosion, where all of those solid molecules then become water, CO2, or nitrogen gas, and you're going straight to a gas, and your temperature is really increasing the entropy as well. And then thirdly, you've got a hot gas, and it's in a small space. So if you think about an explosive shock wave, it goes through the material and turns everything to a gas, but there hasn't been time for the volume to change. So you've taken something that was really dense, a solid, and if you look at densities, the densities of solids are grams per mil, basically, like water, okay? Gram per mil. If you look at the densities of gases, it's grams per liter. So that's 1,000-fold increase in volume. And that's at the same temperature. So then you add temperature in, and it's even a bigger gas expansion. So that's where an explosive gets its power, is a lot of related to entropy going straight from solid to gas, and then the expansion of that gas, especially at a higher temperature. So in terms of these state functions, these are, we're going to compare this inexact differential versus exact differential. So work and heat, we've talked about, are not state functions. They're path dependent. And so they can't be simplified to delta Q and delta W like the state functions can. So because their integration is path dependent, if I go from a certain pressure, temperature, volume point to another pressure, temperature, and volume point, I have no idea how much work or heat was done unless I know the path. Was it an isothermal path? Reversible? Was it not reversible? Those paths will give different work values and different heat values. So I can't just take delta T, delta P, and delta V and know how much work or heat was done. I actually have to know the path. Whereas for exact differentials, internal energy, pressure, volume, temperature, enthalpy, Gibbs energy, Helmholtz energy, all of those are state functions. All I need to know is the NPT points, the number of moles, the pressure, the temperature, and the volume. And I can tell you what the change in internal energy was, what the change in enthalpy was, entropy, and all of those. Okay, these are exact differentials. I'll show you what that means on the next slide. And they can be simplified to delta U, delta P, delta T, etc. Okay. We're going to go pretty quick. So this is what we mean by exact differentials, that if I have multiple changes occurring, like a change in volume and a change in temperature, I can operate on a state function, this equation of state, and it's pressure as a function of volume and temperature. Well, I can write that. I can take the ideal gas law and write pressure as a function of volume and temperature. And in this case, we're going to take that volume divided by N and call that the molar volume. That's a common thing to do. So when you see this little VM, that's molar volume. So liters per mole. So we put that state function in here. We take the derivative with respect to volume, okay, first. And this T here, this is a partial. So sometimes people ask, what's that funny looking D? That's a partial derivative, okay? So we're taking the derivative of this function with respect to volume, keeping temperature constant. So even though temperature is one of our variables, we're going to treat it as a constant for this differentiation, okay? And so we differentiate that with respect to volume. We end up with this. So there's v to the minus 1, so the minus 1 comes out front, and then we decrease that exponent one more, and so it goes from minus 1 to minus 2. So now it's v squared in the denominator. Now we take the partial differential with respect to temperature and keep volume constant. So we treat volume as if it's a constant, so we end up with this minus r over v squared. So this is what this is just taking the derivative with respect to volume and temperature. We have two variables, and so this is called the total derivative. If we have two variables, v and t, we need to differentiate with respect to both variables. That's the total differential. Now, which do you start with? Now, that's the property of exact differentials that says it doesn't matter which you start with. So let's do it in opposite form, or opposite order. We'll do temperature first and then volume. So we differentiate this with respect to temperature. We get r over Vm. Then we differentiate with respect to volume, and we get minus r over v squared. Same answer. So that's the property of, when we say exact differentials, that's one of the properties. Now, are we going to use this in this class? Not so much, because you guys didn't go through multivariable calculus, okay? And so that turns this into a calculus course if I try to teach you calculus and do all of these. So we're going to just do a survey of these different thermodynamic properties that come out of these partial differentials. So let's look at some of these. So we have the volumetric expansion coefficient. This accounts for the change in volume with respect to temperature. So if we take an equation of state and we differentiate it with respect to, differentiate the volume, so we write it as, volume, which we'll do these in a sec. So you have V equals N RT over P, right? And we differentiate that with respect to temperature, keeping the pressure constant. we end up with that volumetric expansion coefficient. Okay. And this 1 over V per term is in the front. So that again is this is given the term beta, and it's units of inverse Kelvin because the volumes cancel. Okay. Then we have the isothermal compressibility. We'll talk about each of these individually here. I'm going pretty quickly though. And so this accounts for the volume change with respect to pressure. So if you press on something, does it shrink? How much does it shrink? That's what this is about. Okay. So if you press on a gas, it shrinks. If you press on a liquid, not so much. So the isothermal compressibility for a gas is huge. The isothermal compressibility for liquids and solids is very small. Same up here with the volume change with respect to temperature. Gases expand a lot with respect to temperature. It's linear in temperature. But the solids and liquids expand just a little bit. And in fact, you can take materials that have almost no volumetric expansion coefficient, very, very small ones. Then the Joule-Thomson coefficient, this is a really good one because this is the change in temperature with respect to pressure at constant enthalpy. So if we expand a gas or change the pressure surrounding that gas, we can get a drop in temperature. And this one is useful for refrigeration. So all of our refrigeration and heat exchange is, depending upon compressing or expanding gases, our heat pumps, depend upon the Joule-Thomson effect. And then lastly, there's this internal pressure, which is really a strange thing. I hate that it has units of pressure because it actually makes more sense to think about what the partial actually tells you. This is the change in internal energy with respect to volume. So what is that? That is intermolecular attractions.
Can you say that one more time?
It's the change in internal energy with respect to volume. So if I expand, like take water, you got a water molecule in a liquid, and I expand that liquid so much that now the water molecules are so far apart. What have I had to do? I've had to break all of the hydrogen bonds and all the polar interactions and all the dispersion interactions. So this is the change in energy with respect to volume, and that's our intermolecular attractions. So when we get to the Hansen solubility parameters, this is what we're going to be talking about. So here's a little survey of these. I calculate them for an ideal gas over here on the left. And so this just says that an ideal gas would expand about 8.2% per Kelvin. Here's our solids up here, and liquids. And this number, this is something that we need to figure out. Oh, and this is also look at this table, the way this is written. So this is saying that 18.9 is equal to 10 to the 6th Kelvin to the minus 1, okay? Which is beta in those units, okay? And so if we want to know what beta is, we've got to divide both sides by 10 to the minus 6. So beta is equal to 18.9 times 10 to the minus 6 per Kelvin, okay? It's in, and this little slash means it's in the units of Kelvin minus 1. So that's saying that these are really small amounts. So silver is going to expand only 18 parts per million per degree Kelvin. And that's good, because if I put silver in my teeth to fill a cavity, and then I drink some hot coffee, I don't want it expanding, because that'll push on my nerve and make me go crazy. Yeah, so this thermal expansion is really an important property in some areas, like dentistry. Okay, and other places too, like Pyrex glass. You know, you set it on the hot stove and the bottom expands, but the top doesn't, then the glass shatters. You know, so, or not just the stove, but our beakers and Bunsen burners. You know, so Pyrex has almost a zero isothermal expansion coefficient. Here's isothermal compressibility. So how much does it change per atmosphere? So if you push on a gas, you add a whole nother atmosphere of pressure, it's going to change by 24.4. And so it's going to be huge. Whereas if you press on aluminum, let's use a liquid this time. Let's take, let's do mercury here. So again, that's going to be kappa is equal to 3.91 times 10 to the minus 6 per bar. So if I push on mercury, its volume is only going to change by 3.9 parts per million at 3.9 times 10 to the minus 6. So if I have that in a tube and I push on this end, it's not going to absorb much of that pressure. It's going to deliver that pressure to the other end. And this is how hydraulics works. So if you have a liquid in a tube and say one end of that tube is a piston and you push on this end of the liquid, it's going to push that piston. And the tubes can go around corners and all kinds of places. So think of all your backhoes and tractors. You have a hydraulic pump that pushes on that liquid, and that pressure goes through the liquid. If your liquids were compressible, then your energy would go into compressing the liquid, not pushing the piston. And so the incompressibility of liquids is how hydraulics works. We push on one end of the liquid through a tube, and it pushes all the way out the other end of the tube, and it doesn't absorb that pressure inside. It doesn't compress. You can do pneumatics. You can push on gases, but it's not as efficient as liquids. It generates a lot of heat. And so the Joule-Thomson coefficient is measured this way. So as the gases expand through this little frit, they cool down. And so you can look at these thermocouples and you can see the cooling upon expansion of a gas. So the gases go through this little sintered glass or sintered metal thimble, and you can measure the amount of temperature change, and you can measure the Joule-Thomson coefficient. I'm going to get past this to get to the last slide. This Joule-Thomson coefficient tells us where the regions of cooling and heating are, because some gases, when they expand, they actually heat up. And that's because of the pressure regime. Notice the x-axis here is pressure. So at high pressures, you can have gases so close together that when they expand, they actually relax and they give off heat. And that's not cool. Here's what's going on. If we are in a sort of average distance between gas molecules about here, and we expand them, there's not much difference. If the molecules are on an average this distance and we expand them, then in order to rip them apart, it takes energy, right, for them to move up to this fully apart area. And so that energy has to be supplied. So heat has to go into the system to raise the temperature. But if the gases on average are up here, and then you expand them, then the system releases heat. And so that's how the Joule-Thomson coefficient can invert when we go to high pressures. And we're out of time. But anyway, I hit you with a lot of stuff today. Mainly it was just a summary of these different properties that we get from thermodynamics, like expansion coefficients, compressibility factors, and so on, and how they relate to dentistry and cooking and hydraulics and tractors. And even we did our first cycle today of engines. So, a busy day.